In this video, we're going to prove the intersecting chords and secants formula. So this AX times BX equals CX times DX. We're going to prove this formula here. So it all starts with the chords. We'll deal with the chords first, right? If we take our two chords and split it up like you see here, I can create two triangles. Okay, so AX there I've just highlighted in red. CX I'm highlighting here in green. Go with DX here in blue, and then orange for BX. Now what I've then done for this extra side here is I've joined these ends of the chords up. So I'll put lime green, AC like so. Okay. So just to highlight, you have two chords, they intersect each other, and then I've joined up the ends to create two triangles. Now these triangles happen to be similar triangles because by our circle theorem, angles in the segment are equal. Those two angles that I've just highlighted there are both equal. So I'm going to call this little e, and I'm going to call this one little e to signify those two that I've just highlighted there. Okay. Similarly, if I look at this upside down, these two angles here are also both equal by the same rule. Angles in the same segment are equal. So that means, picking a different color, well, I've got too many colors now, that these angles here are F. Now, if you've got two angles that are the same size as each other in a triangle, then that means that the leftover one must also be equal. But just to kind of prove that, here, if we look at this angle here in yellow and this one here, vertically opposite angles are equal. So just to confirm, we'll call it G, that all three of those angles are equal. Okay. Now, the main reason why I talk about this is because the fact that all three angles are equal, just going to erase all that now, means that these two triangles that we have are similar. Okay. We're dealing with similar triangles here in such a way that if you take one length and divide by the corresponding length in the other triangle, so the ones that go together, then you're going to end up with a scale factor. And how that's going to work here is that the lime green length, if we divide that by the pink length, then we would get a scale factor. If I do the same with the red length divided by the blue length, I'm going to get a scale factor. And if I take the darker green length and divide it by the orange length, I'm also going to get the scale factor, because all I've done here is pick the three lengths of this triangle and divide them by the corresponding lengths in that triangle. Big divided by small will give me a scale factor. So all of these things are equal to each other in terms of their colors, okay? But now to clarify exactly what these colors were, well, the red line was AX, the length of AX. The blue line is the length of DX. The dark green line is the length of CX, and the orange line is the length of DX. And I'm not technically interested in this green and pink one here because they aren't chords. So that pink and green line, let me just erase them now. They weren't part of the original picture, but they're used in terms of this proof. Once I've got this formula now, hopefully you can see straight away that all I then have to do is multiply dx over and multiply, sorry, I've wrote something wrong here. That should be a bx on the bottom there. So I'll say that again. If you multiply both sides by dx, it will pop up over there on the right. And if you multiply both sides by bx, I've erased it again, then that will pop up over there on the left-hand side. And basically from there, you're going to end up with this formula here. AX times BX equals CX times DX. So that's the proof involving chords. The proof involving secants is quite similar. You have similar triangles again, just to kind of briefly go through this. If I connect B and C like that, that's this length here. If I connect A and D like this, that's that length here. And then I'll join up BX there in red, CX in orange, and no, I've already got pink, light blue for all of this length here, AX, and dark green for all of this length here, dx. Okay. Now the main difference between this is that the similar triangles don't quite line up as nicely as they do in the other one. just to highlight, if we know what this angle is here, let's call it Q, then the angle on the other side here would be 180 minus Q. So I'm just going to highlight here that this is Q, and then this would be 180 minus Q. And then using the circle theorem, opposite angles in a cyclic quadrilateral add up to 180. If this angle here is 180 minus Q, then that means that this angle over here must be Q. So that gives us this angle Q and this angle Q. Those are similar to each other, okay? Which means that the red side here corresponds to the green side here, because Q is this angle here, Q is this angle here, and they both share an angle there. So basically the length between, let's call this P, angle P, the length between those two angles in each triangle correspond to one another. Now if we go down a similar road with doing it on the other side, so we're going to raise back to, so if we do the exact same thing on the other side, except I call this one Q now, then we have 180 minus, then opposite angles in a cyclic quadrilateral end up there. Then we end up with another pair of angles that are equal. So we have our two Q's like this. We have our other two angles, let's just call them P. And then lastly, again, because this angle is shared, we have the same principle as before. We have that the three angles in both triangles are all identical to each other. The three angles in one triangle are the same sizes as the three angles in the other triangle, which means that these two are similar. And setting up similar triangles again in a way that we did before, our dark green length divided by our red length is going to be the same size as our blue length, our light blue length, divided by our orange length. And again, just like last time, I'm going to get rid of the extra pieces that we didn't need, so the pink and green I don't care about from now on. When we set these equal to each other, because they both equal the scale factor, the scale factor being big divided by small, we then just need to highlight what these colors were again. Green in this case is our dx, red is our bx, blue is ax, and orange is cx. Then if we multiply cx across, we'll end up with cx times dx on the left-hand side. And if we multiply bx across, we're going to end up with ax times bx on the other side, which is exactly the same thing as this, except the c's and d's are on the left and the a's and b's on the right. Proven. Done.